Okay, guys, so here's lecture 2 on chapter 8. We're still dealing with the idea and the concepts of energy and free energy, and specifically, we had just finished on the laws of thermodynamics, and now we're going to really talk about how this energy within our systems really works. So, when we talk about free energy and the idea of spontaneity, remember, spontaneity is anything that's going to naturally release energy to create or to increase the entropy in the environment. Okay, so that's when a spontaneous reaction really is. The free energy, however, is referring to the energy of the system when we don't consider the energy leaving to the surroundings. In other words, the free energy is the amount of energy available within the system under study that can be used for work. Okay, so we're going to designate free energy as delta G. G is named after the guy Gibbs who discovered this. So it's usually called Gibbs free energy equation. But in this case, free energy, or delta G, the change in free energy. Remember, that's in reference to the system excluding its surroundings. So we just want to know how much energy is available in a system to be used to do work. Typically, in a uniform or in a system like a living cell, we assume that the temperature and the pressure are going to be relatively uniform, so they don't really play too much of a role in what's happening, but we still have to account for the temperature. So when we deal with this idea of the free energy equation, we're going to say that the amount of free energy, or delta G, the overall change in free energy, is going to be equal to these variables. Delta H, which is known as enthalpy, the amount of energy available, minus this combination of terms, T delta S. T delta S is simply the absolute temperature given in Kelvin. You guys saw that from your first lab. And delta S being a measure of the entropy or disorder. And so if you take into consideration the amount of free energy that's available, we're taking into account the amount of energy or enthalpy that is in the system, and we're going to remove from that the temperature times the amount of disorder. So for example, if you have an increase in temperature or an increase in disorder, this whole part of the equation is going to increase, thus we're going to lead in a more negative delta G. However, if the temperature is low and the entropy is, and there's low entropy or low disorder, then the amount of free energy available to work, delta G, will be high. So essentially, it's a balance between these two terms. If we decrease the amount of enthalpy, but we increase either the temperature or the delta S, or the entropy, that means we're going to get a negative delta G. On the flip side of all of this, if we increase the temperature or entropy of the system, and there's less available energy within the system already, or enthalpy, then we're actually going to end up getting, I'm sorry, I said that wrong. If we decrease the temperature and the entropy and increase the amount of energy that's in the system already, or the enthalpy, we're going to get a positive delta G. So essentially the ideas behind all of this is that we have to incorporate all of the changes of heat and disorder to the overall flow of any given metabolic process. And we're dealing with the idea of free energy. We have a special terminology associated with these, of course. We have what are known as exergonic and endergonic. Think of exer as exit. Okay? An exergonic reaction, this is terrible. An exergonic reaction means that free energy, or energy in general is going to be released from this reaction. So our delta G is actually going to be 0 because there'll be less available energy of the system after the reaction has occurred. So any exergonic reaction is going to be releasing free energy. And again, that free energy is the energy available within the system, and typically we deal with the free energy or the energy that's in the system as what is in the chemical bonds. Exergonic reactions will release energy. They are considered to be spontaneous. And that means our delta G is going to be low or essentially less than 0 or a negative value. On the flip side of that, of course, would be an endergonic reaction, or energy has to be put into the system in order for the reaction to occur. Okay? So an endergonic reaction needs energy input. And I'm hoping that you're also starting to understand that an exergonic reaction is something that we're going to consider being catabolic, releasing or breaking down of something to release that energy. So this is going to be catabolic, these exergonic reactions like cellular respirations. And endergonic is going to be something like photosynthesis or an anabolic reaction where energy input is needed. Okay, so let's quickly summarize what I've said so far in this slide. Free energy is the amount of energy within a system in reference to on its own, not considering the surroundings. It's the amount of energy available to do work, whether it's a cell, a tissue, so on and so forth. Any chemical reaction that occurs is going to alter the amount of free energy. The amount of free energy available has everything to do with how much energy is already there in the system or in the bonds, the delta H, that enthalpy. And we want to also consider the temperature, because remember, if it's an increase in temperature, there's going to be more kinetic energy, and that should lead to more disorder. And the delta S, which is essentially the entropy or the disorder in the system. When we have a high temperature or a lot of disorder, it's going to make this component of the equation a large number, but since we're removing it, it should result in a negative delta G. And we're going to call that an exergonic reaction. Spontaneous and energy is being released. So we're breaking chemical bonds. It's a catabolic reaction. We are breaking down biomolecules like a hydrolysis reaction or breaking down glucose. In terms of the endergonic reactions, that is when the amount of energy that's there in the bonds, this delta H, will be greater than the temperature and the entropy combined. So when we have a high amount of energy that's there, or we're adding energy into these bonds, we're going to have a large delta H, and that should give us a positive delta G. Any reaction that requires an input of energy is going to be referred to as endergonic. These are going to be the anabolic processes that we've been talking about, where energy is put into the reaction. So energy input is needed. So real quick and real simple, an exergonic reaction will release energy. It's a catabolic reaction. It's a breakdown, where the products will have less free energy than the reactants. So our delta G will be negative and has released energy, and we consider that spontaneous. In an endergonic reaction, there requires an input of energy, where our delta H value will be high. An endergonic reaction is an anabolic process to build things up, where energy input will be needed. It's important for us to understand that all systems are attempting to sort of achieve this energy coupling, where all exergonic reactions and endergonic reactions sort of balance each other out. And in this section, we're really going to see how that is done, or how that is accomplished by the incredible molecule ATP. Knowing the delta G of a reaction gives us a lot of prediction to determine the types of changes and how we can harness these changes to do work. It's important to note that if there is an endergonic reaction, we're going to actually need an input of energy. And if there's an exergonic reaction, we're going to need a place to put that energy. Okay, and the resolution and the answer to all of this is all going to be dealing with this idea of energy coupling. Now, for example, this is going to be a reaction. We can see this as the delta G is negative. So this is, of course, glycolysis, or the breakdown of glucose. Actually, this is cellular respiration. Excuse me. This whole equation here. Oh boy, what's happening? This entire equation here is cellular respiration. Okay? And we know that in cellular respiration, there's going to be a release of 686 kilocalories per mole. Notice how it's a negative value. It means that at the end of cellular respiration, that's how much energy is going to be released. So that system of a glucose molecule no longer has the 686 kcals per mole. And we're going to need to do something with that energy that was released. Free energy in metabolism. Again, endergonic absorbs G, free energy, from the surroundings, so that requires an energy input. And you'll notice that I have ATP listed here as the molecule that's going to provide that energy input. We store free energy in the molecules. So an endergonic reaction is a positive delta G, and it's considered to be an uphill or anabolic reaction. Consider if you're going to push a boulder up a hill. You're going to have to put in a lot of energy to push that boulder up. That's an endergonic reaction, an input of energy. At the end, when that boulder is at the top of the hill, it has a lot of stored free energy, or has positive delta G. And it required an input of energy from us by using our legs to push that boulder up. And of course, that input of energy for any endergonic reaction will come from the ATP molecules. An exergonic reaction, of course, is the release of free energy out to the surroundings. An exergonic reaction generates ATP. So that's the interesting thing here, is that exergonic reactions, in other words, when we break down biomolecules, when we are breaking down glucose, when we break things down via hydrolysis, the release of that free energy is going to be used to make ATP, generate ATP. So that release of free energy from the molecular bonds is going to be known as the delta negative G, as you can see this here. And this is considered to be a spontaneous or downhill reaction because it's going to end up being more free energy and more disorder. So we've got the blue arrow. If you can see the blue arrow here, that would be an indication of an endergonic reaction where there's going to be an input of energy to store the free energy up here. So this is going to be a positive delta G. Oh, and of course, there is no fancy-dancy symbol up here. So this is going to be a, we'll just say, positive delta G with the blue arrow. I can spell positive delta G. Because glucose has a lot of, so that's that positive delta G here, this endergonic reaction. However, when we break glucose down, we know that this is going to release energy, or release free energy out to the environment. So there's going to be a negative delta G at the end of this reaction. And I think it also makes sense, too, that you can see that there's one molecule of glucose up top, and there's 12 molecules seemingly so down here, which indicates the idea of the uphill, downhill. And, of course, negative delta G means that there should be an increase in entropy or disorder, and that's our delta S. Okay, so once again, to summarize in this slide, endergonic absorbs free energy from the surroundings, and that's going to be from our ATP molecule, an input of ATP, so the energy input from ATP to store delta G, giving us a positive delta G in our uphill reaction. exergonic energy is going to be released to the surroundings so that we can generate ATP. That's going to be the negative delta G that we've been talking about. I'm hoping that you're starting to understand that exergonic reactions require ATP, okay? And exergonic reactions generate ATP. So in a sense, when we talk about the idea of coupling exergonic to endergonic reactions, we have to consider this all-important molecule, ATP. Okay, so I think that we're getting a good understanding here. And here's a nice schematic. What I'll do is I'll shrink down one and sort of go over them in detail individually. So here, if we've got free energy and spontaneity, you can clearly see free energy on the Y, the progress of the reaction on the X. And you can see that the reactant molecules here have a much higher amount of, what am I doing? The reactant molecules here, oh, brilliant. The reactant molecules have a much higher amount of stored energy. At the end of this reaction, you can see that energy is released here. This is an exergonic reaction, and the energy of the products is less than the energy of the reactants. And you can see that the decrease in free energy, or the amount of energy released, gives us a negative delta G. On the flip side, those reactants, when we have to add energy to the reactants, low energy at the beginning of the reaction, adding energy, which means it's endergonic, means that the products will have a higher amount of free energy in them at the end than compared to the beginning. So the products have more free energy than the reactants. Thus, this is an endergonic reaction because we end up with a positive delta G. Any endergonic reaction is non-spontaneous because it requires an input of energy. It's not a natural happenstance. To make order is against the laws of thermodynamics. So these endergonic reactions require an input of energy. Exergonic reactions go with the idea of this order or entropy, and so they tend to release free energy and are considered to be spontaneous. What it all boils down to is that we're attempting to get our delta G at a point of equilibrium, where within a system, the amount of exergonic reactions that release the energy are going to be coupled with the reactions that actually require energy. So there should be an equal amount of energy releasing and energy absorbing reactions so as to sort of get into this nice little equilibrium where our delta G, the amount of free energy available, is actually zero. Not because there isn't any available, but because our cells are so efficient that as we release free energy, we are using it to do work. As exergonic reactions are used to break down things and to release that free energy to do cellular work, our cells can absorb that energy to do endergonic processes. And that's the idea. It's not that we're trying to not have energy, it's just that we want the exergonic reactions to be balanced with the endergonic reactions. Free energy is a measure of instability. Okay, so if something is a negative delta G, we know that it's going to be more stable, whereas a positive delta G means that it would be unstable because there's too much free energy there. So a spontaneous reaction will have less free energy in the final state, and it's unlikely that those products are going to change again because all the energy has been released. So our goal is essentially to release energy and to get to where our delta G is approaching zero. So all of our spontaneous reactions are going to move our system towards a more stable state because the energy is going to be released. Everything is brought down to its initial state. It's a downhill reaction. As this occurs, we are hoping to balance out the free energy initially with the free energy at the final, so that overall our delta G is going to keep approaching zero. All of our exergonic reactions should be balanced by endergonic reactions. I have no idea what is happening right now, so I will shrink that down. Sorry, guys. A process is spontaneous and can perform work only when it is moving towards equilibrium. So we're trying to maintain order. We're trying to maintain equilibrium. We really want the balance to occur. We want any energy that's available inside of our molecules to be used to do work in the cell. That's that equilibrium state. Well, then how does ATP work into all of this? Well, it's kind of straightforward, so try not to overcomplicate it. Adenosine triphosphate. I think that we had mentioned before the structure of ATP being extremely important to overall cellular work. There's mechanical work, transport work, chemical work, you name it, our cells have to do it. And we can only do this sort of delta G equaling 0 type situation by coupling exergonic with endergonic reactions. And we can't do that without this awesome molecule ATP. We need to couple exergonic processes with endergonic processes. And ATP itself, therefore, has to undergo both exergonic and endergonic reactions to couple the overall exergonic and endergonic reactions within our cell. So here's the structure of ATP, but the reality that what I really want you guys to pay attention to here is the idea of our triphosphate groups. Oh boy, this is going to be a mess. Yeah, that's sloppy. That is also sloppy. My apologies, guys. Oh, it's much easier when I'm on a smartboard, but clearly I'm not there today. This, oh, come on. Let's make a circle. That's not a circle. Let's make a small circle. Wow. Oh, well, that works. Here's the key, guys. These three phosphate groups, all of these oxygens, okay, are highly electronegative, and they do not want to be near each other. There's a lot of negativity there, but those phosphate to oxygen bonds are rather strong. So you've got the phosphates and the oxygens pulling the phosphates together, okay, or the phosphorus to the oxygen bonds are pulling them together, but the oxygens are pulling them apart. So each of these phosphate groups is kind of vibrating like this towards the end. And that's a lot of stored potential energy. To make ATP, energy must go in. And when we break ATP, energy is going to be released. So I think that you start to understand when we talk about the energy, where are we going to put the energy from our exergonic reactions? We're going to put the energy here in the triphosphate bonds. How are we going to distribute that energy to our endergonic processes? Well, we're going to be releasing it from these triphosphate bonds. Essentially, to make ATP requires an input of energy from our exergonic reactions. So exergonic reactions from the cell will fuel the endergonic synthesis of ATP. To fuel our endergonic reactions in the cell, we will have to break down ATP in an exergonic process. And that's what I'm about to show you. Keeping in mind, guys, the idea of hydrolysis in the sense that when we perform hydrolysis, we are splitting apart molecules, and it's an exergonic process. We are breaking things down. This is catabolic. There is an amount of 7.3 kcals of energy. In other words, this is going to be released. This is a negative delta G. The hydrolysis of ATP releases 7.3 kcals. So this is a negative amount of delta G. Energy is being released. This is an exergonic process. The process highlighted here is an exergonic process. We're releasing free energy. So if this exergonic hydrolysis of ATP releases 7.3 kcals, the required delta G for any endergonic reaction can be satisfied by these 7.3 kcals. So what this sentence is saying, oh, and I don't know how to spell, oh, that's really weird, hydrolysis if the delta G of an endergonic reaction, in other words, the energy input reaction, if the delta G required for that reaction is less than 7.3 kcals that are available in ATP, then these two reactions can be coupled via what is known as phosphorylation, or the adding of an inorganic phosphate group. The P sub I is indicative of the inorganic phosphate group. It's not attached to any organic molecule. This down here summarizes the idea. Here's ATP. We're going to break the bond. We're going to break this third bond, and in the process, we're going to release 7.3 kcals. But remember, it's released, so it's negative. So the hydrolysis of ATP is an exergonic reaction, and we're releasing 7.3 kcals of energy. This energy can then drive endergonic reactions from the cell, and I think this next slide is going to really drive it home. Let's take, for instance, forming glutamine by taking glutamic acid and adding it to ammonia. This reaction would normally require an input of 3.4 kcals of energy. That's going to be an endergonic reaction. I think you all understand. If there's a positive delta G, we know that it has to be endergonic. That's a terrible N, but endergonic reaction. Okay? All right, that's just horrible. Let's just go ahead and type endergonic. Okay? When we look at coupling this reaction with ATP, you can see that glutamic acid is here, ATP is there, but the ATP uses to phosphorylate the glutamic acid. That phosphorylation is not just giving the inorganic phosphate, it's giving that glutamic acid energy, an input of energy, because this reaction of ATP being broken down is exergonic to fuel this endergonic. So, once again, this process of ATP, what is happening? This process of ATP phosphorylating the intermediate, that is an exergonic process. It's releasing energy. Remember, though, that the overall equation that we're trying to deal with is an endergonic process here. Then, the amino group can be added, and we form our substrate. And notice that we form our glutamine, and we've got ADP and the inorganic phosphate at the end. So when we look at this all together, here is our reaction, glutamic acid plus ammonia plus ATP, because we know that to make this reaction happen, we need 3.4 kcals per mole. When we break down ATP, or the exergonic reaction here, this exergonic reaction is releasing 7.3 kcals per mole. This 3.4 required for the reaction is less than that that's being released from the exergonic reaction. Therefore, we can do this endergonic reaction by fueling it with the endergonic hydrolysis of ATP, and we still end up overall at the end with a negative delta G. So this shows that by using ATP, we can drive or fuel the endergonic reactions, and still, overall, at the end, we get a net negative delta G. So even though this is an endergonic reaction, when we couple it with ATP hydrolysis, we still are adding to the entropy in the universe, as you can see here. So what does this mean overall? I'm going to shrink this down so we can do a little bit better job. Just kidding. No. Here we go. Okay. exergonic reactions. So we are going to break down biomolecules, and exergonic reactions are going to release energy. So this is going to be negative delta G. Exergonic reactions. Do y'all get that? That this is a release of delta G. Negative delta G. Okay, exergonic reactions, negative delta G. To make ATP from the inorganic phosphate and ADP, this process, I hope you understand, is not a negative delta G, but it's actually an endergonic process, and therefore requires an input of energy, or is a plus delta G. This over here is exergonic. This process of making ATP is endergonic. That's an endergonic process. And so we end up having an exergonic reaction drive the endergonic synthesis of ATP. Is everybody still with me on that? Well, we know that cellular work requires an input of energy. These endergonic processes require an input of energy. That's what I'm showing. Whoa. That's what I'm showing you over here. In order to fuel these, I know I just waved my hand, maybe you can't see what I'm showing you here, and I do apologize, so I will try to swing this over. We've used the exergonic reactions from our cell, breaking things down. We've released that energy, and that drives the endergonic synthesis of ATP. But we've had exergonic reactions in our cell. We still have endergonic reactions that we need energy for. And we're going to get that energy from ATP. The breakdown or the hydrolysis of ATP, we know, is not an endergonic reaction, but it is an exergonic reaction, which means we are going to release energy here. That release of free energy can be used to drive the endergonic reactions inside of our cells. Here's the bottom line. Exergonic reactions inside of our cells release free energy, a negative delta G. We use that free energy and we temporarily trap it and store it by the endergonic synthesis of ATP. Exergonic reactions drives the endergonic synthesis of ATP. The exergonic hydrolysis of ATP then fuels the endergonic work inside of the cell. ATP can couple exergonic and endergonic reactions to achieve equilibrium because ATP itself undergoes endergonic synthesis and exergonic catalysis. In order to make ATP, it requires energy. In order to break ATP, it's a release of energy. And so what this really means to everything is that ATP couples all of our cellular processes. Okay? The G, that free energy that's used to phosphorylate this inorganic phosphate to ADP, comes from the exergonic breakdowns or our catabolism. Then it allows for ATP to release the energy back out. ATP can couple exergonic and endergonic reactions because ATP itself undergoes endergonic synthesis, and exergonic catalysis. ATP is a renewable resource that can constantly be regenerated. This is the nutrients. These are the molecules that are cycling in the ATP-ADP cycle, so that energy can move one way through. This slide is simply restating what I just said, so I'm just going to let you, you can pause on this, but I'm not going to reread it. And once again, this is just reinforcing what I just said, is that by breaking down ATP, it gives us the energy that is needed to fuel these processes. And I think this is probably a good place to stop. This just shows you how we couple these and still end up with energy being released. Okay? Here, we need to go reactants A plus B. We realize that it's going to be an input of energy, so it requires a positive delta G. But we're going to use the release of free energy from our exergonic breakdown of ATP to drive this endergonic process. So this whole thing is ATP releasing its energy to drive this endergonic process, so that at the end, our products are molecule AB, an inorganic phosphate, and ADP, or adenosine diphosphate. Okay, and so with that, the energy released from ATP can be used to increase order in a system, and this is how I'm going to leave this lecture, and I will start the next one in a little bit.